today over kind of the history of the atom, going through this idea of this evolving structure. All started back with the ancient Greeks. One guy in particular, Democritus, it was his idea, keyword there, idea. He was a Greek philosopher, so he had no scientific evidence to back this up, but his idea was that you could cut something down piece by piece and just keep cutting it in half until you get to something where you can no longer cut it. It's uncuttable. And he called these atomos, or we get the word atom, meaning uncut or indivisible. Now, there were other theories in the day, and those theories actually ended up winning out from other philosophers that matter was continuous, that you could just keep cutting. But Democritus is credited with the first kind of idea of the atom. So 400 BC, don't need to know a whole lot about the dates. You don't need to memorize those. Just kind of showing you the timeline. So early 1800s, 1803 I think is the actual date. But John Dalton, he brings back the idea of this particle, this thing that's uncuttable. And he actually conducts experiments to prove this using gases. And what he comes up with is kind of the first modern atomic theory, so something based around atoms. And his theory, depending on what book or what text you look at, has 4 or 5 parts. They all mean the same. Some people condense them. The one I'm going to give you has 4. So matter is made up of these tiny indivisible particles called atoms. The second one, all atoms of an element are identical in mass and properties. I'm going to put a star next to that. We will talk about that a little later on. The third one, atoms of different elements combine in whole number ratios to form compounds. What it means by whole number ratio is that you have, if it's water, you have 1 oxygen, 2 hydrogen. You're not having parts of atoms come together. And then the last one, chemical reactions are the rearrangement of atoms. They're not transforming into different elements to make these other compounds. They're just rearranging, breaking bonds, forming new ones, not creating and destroying. Up next, J.J. Thomson, and so again, getting closer to 1900 now, used a cathode ray tube, and these, it's a beam of light. I'll show you a picture here in a second, but what it is, it's this gas tube, and it has 2 plates on each end, and I guess it looks kind of like this, where gas tube, they suck all the air out, so there's nothing in here. And then there's a couple of plates, and between those plates, they shoot electrons. And then what he did was he put a couple of magnets, or in this case, some magnetic plates that he could turn on and off and flip around. But what he noticed was when he shot electrons through, when he turned the positive one on up here, the beam of light kind of pulled towards it. And then kind of in a second experiment, he tried, I recopied the same picture, but it would have been kind of the opposite. If the positive plate was down here, the electrons would be pulled towards that positive plate. Well, in science, we say opposites attract. So what he found was that these electrons, or he didn't know it, but these particles, they had this charge, and that charge must be negative. It's always attracted to the positive side or reflected from the negative side. Later, he finds out that these particles actually have a mass smaller than that of an atom, and so we get the first subatomic, so the first thing smaller than the atom. Up until then, we thought the atom was the smallest thing, but now we have something that's subatomic and has that negative charge. It's known as the electron. next up, so a few years later, Ernest Rutherford comes along, and he's famous for what we call the gold foil experiment. Looks kind of like this, where you just have a box, and that box has kind of just a slit cut in it. And inside that box, there's a piece of radioactive substance. I don't know what he used, but it shoots out these things called alpha particles. Well, the alpha particle, it doesn't shoot them out. They bounce around, but the only place they can leave from is that slit. And so as they leave through there, what he thought was that these particles were just going to come straight through the gold foil and light up his detection screen. So this, I don't know, made of kind of a fluorescent screen. So when you give it energy, it lights up, it glows. So he thought he'd just get a whole bunch of spots to glow right back here, straight through. But what ended up happening was some of those particles, as you can see, were deflected at very large angles, and some even almost like right back towards the screen. And you know, he was correct that some of them did, but then it was these kind of outliers, the ones that bounced back, that really caused him to think about it. And so what ends up happening is he concludes that, well, they have to be hitting something. And because these alpha particles, because they have a charge, he concluded that there must be this positive region in the middle of these atoms. And it's very dense because it's causing these things to bounce back even. And he called this the nucleus. Inside that nucleus, what's giving it that positive charge, we later find out that this dense positive part, at least the positive part, is the proton. So there's two of our subatomic particles, the main subatomic particles. The last one, the hardest one to find because it doesn't have a charge. So you had the electron, pretty easy to find with that set of magnets. You have the proton, having a positive charge, easier to find because of the way it deflected those alpha particles. But then, so 30 years pass before we actually get something, we get that third particle without a charge. So experiments showed that some terms we'll talk about in the not too distant future, atomic number and atomic mass. Atomic number is the number of protons. Atomic mass is, as we'll find out, it's a calculation, but it's protons plus neutrons-ish. He found that they were different, and before, we didn't know about the neutron yet. So kind of thought about it and said, well, the electron, we know it's so small that it barely has a mass. It has very, very little mass. We even say, in some cases, that it has no mass. He makes the guess that there was this third particle. It was proved later through some experiments that other people did, as well as he replicated. And what he ends up finding then is that the mass of this third particle is very close to being equal. We'll actually call it equal for purposes later on to that of a proton. So, and then since it didn't have a charge, he calls this the neutron. So kind of neutral particle, the neutron. The last little bit here, kind of summarizing each of those particles. The way you'll see me write electron is probably an E-. With that negative charge, we said it has very, very little mass. Relative to everything else here, we say it has zero mass. Actually, 9.11 times 10 to the negative 28 grams, so super, super small. The proton, you see me write it as P positive. With that positive charge, relative to everything else, we say it has 1. And if you look at the proton versus the neutron, very small difference. I mean, way out here with 24 zeros in front, not changing it a whole lot between the neutron. So relative, we say 1 and 1. Neutron, you'll see N naught or N0 with no charge.